Suppose that we have a north pole here and a south pole here. Then in between, we would have a roughly uniform magnetic field. When we are further away on the sides, the fields would be a bit weaker. Let's say the field is 1 Tesla. 1 Tesla. And suppose that around the center of the field, we have a piece of copper wire that is bent into the shape of a rectangular or a square loop. Now, suppose I have these two ends from the copper, this square loop, leading away to someplace outside of the magnetic field. Now I want this because I want to connect these two ends to a voltmeter, so I can measure any voltage that might be induced in the copper loop. Suppose that this square loop, has an area of has a side of 10 centimeters. Now, and I want to rotate this loop in this clockwise direction. Let's say I rotate it by 90 degrees so that the vertical loop becomes horizontal, like this. Okay. Now, and suppose I do that in a very short time. I do that in, say, 0.005 seconds. Okay. Now, what I want to do now is to calculate the voltage induced in the loop. So, using Faraday's law, we know that this voltage V is equal to the change in the flux linkage divided by the time taken. So here I've used delta to represent change. The two triangles, that means change. Now, and I can actually calculate this because let's say I take this magnetic, I represent this magnetic flux density by B, and let's say that the area of the loop is A. Then the flux would be B times A when the loop is vertical. And when it rotates and becomes horizontal, when the loop becomes horizontal, you see that the field lines actually pass above or below the loop, and that when the loop area is horizontal, there's no field lines that actually go through the loop, which means that when the loop is horizontal, the flux linkage is 0. So this just means that it is at first the flux is equal to BA when the loop is vertical, and when it rotates and becomes horizontal, when it rotates by 90 degrees, the flux becomes 0. So therefore the change in flux is simply from BA to 0. And then we would divide that by the time taken. Okay. Now that we know what to do, we actually have the values that we can calculate. The flux density B is 1 Tesla, and the area is the size of the square is 10 centimeter, which is 0.1 meter. So the area is 0.1 times 0.1 meter. Okay. And then we want to divide by the time taken, which is 0.005 seconds. So with this, we can calculate the answer. We find that the answer is 2 volts. So in this way, just by rotating the coil, that means I don't actually have to move the coil away to reduce the flux to 0, I can reduce the flux to 0 in the coil simply by rotating it so that the coil becomes parallel to the magnetic field. So that's what happens when I rotate by 90 degrees. Now what I want to do now is I want to do something, I want to take this further. I want to rotate, starting from the vertical position again, I want to rotate it by 180 degrees this time. So this means that I'm going to rotate, starting from this vertical position, I'm going to rotate not only until it's horizontal, but until it turns back and becomes vertical again. Okay. So that's 180 degrees. And I want to calculate the voltage induced as a result. Now, we know that the starting flux, when it's vertical, we know that it's B times A. When the magnetic field goes through the loop, but when the magnetic field is perpendicular to the loop, the flux is just B times A. Now, when it rotates until it is, when it rotates by 180 degrees, the loop becomes perpendicular to the magnetic flux, the magnetic field again. So therefore, the flux going through the loop is again B times A. So it looks like the change in flux is simply BA minus BA, which is 0. And then if we divide that by the time, the answer should be just 0 volts. But in fact, there is a difference between this BA and this BA. And the reason is this. Now think of, say, one side of the loop. Right? I would use this arrow here to represent, say, this side of the loop. Okay, this arrow, think of it as an object that an arrow that is always at 90 degrees to one side of the loop. Then if I rotate, well, in this position, notice that this arrow is in the same direction as the magnetic field. But if I rotate, if this loop rotates by 180 degrees, this green arrow would then point in the reverse direction. So when the loop rotates by 180 degrees, the green arrow will point in the opposite direction to the magnetic field. Okay, and also notice that, for example, the top wire on the loop, after it rotates by 180 degrees, would actually come down to the bottom. So the loop position has actually changed. The loop position has actually changed. And the correct way then to find the magnetic flux when one side of the loop has changed direction is to say that the flux has changed sign, like this. So this means that we should give an opposite sign to the flux after it has rotated by 180 degrees. So this is the correct way to do it, and if we do it this way, you can see that clearly you don't get 0 anymore. You get minus BA, and that's and the size of that will be twice of BA. So it won't be 0 anymore. Now, suppose that I take it that the time taken is also doubled. The time taken is also doubled. So because I now rotate it by 2 times the angle, so let's say it takes twice as long. Okay. Now if this is the case, I can put in the same numbers as before for B, A, and T, and if we do the calculation, you'll find that we would again get 2 volts.